How does a balanced seesaw move? The full answer to that question will require some careful explaining, but a short answer is that a balanced seesaw rotates steadily about a fixed axis. Now, it's tempting to think that I've just asked a trick question, that a balanced seesaw doesn't move at all. In fact, that it's horizontal and motionless. But the real answer to that question is more subtle. Yes, a balanced seesaw can be horizontal and it can be motionless, but it doesn't have to be. What a balanced seesaw does exhibit, however, is rotational inertia. If I set it spinning, it rotates steadily about a fixed axis. Up until now, I've talked about a type of motion that takes you from place to place. So in the episodes on skating, falling balls, and ramps, we went somewhere from place to place. In this episode on seesaws, we don't go anywhere. Seesaws are installed in playgrounds and they stay there indefinitely. What seesaws do, however, is rotate. So, the world of motion can divide into two main types. The motion of translation, of going somewhere, and the motion of rotation, spinning in place. And seesaws, they're about spinning in place. In the episode on skating, we saw that a skater exhibits translational inertia, the inertia of going places. And associated with that translational inertia was Newton's first law of translational motion, namely that an object that's free of external forces moves at constant velocity. In this episode on seesaws, we're looking at objects that can exhibit rotational inertia. When they're at rest, they stay at rest. When they're rotating, they continue to rotate. Associated with rotational inertia is another Newton's first law, but now it's the Newton's first law of rotational motion. In a draft form, Newton's first law of rotational motion states that a rigid object that is not wobbling and that is not experiencing any outside influences rotates about a fixed axis, turning equal amounts in equal times. That law has a couple of extra words in it. It refers only to rigid objects and objects that are not wobbling. So Newton's first law of rotational motion has relatively limited applicability. What can you do? Rotational motion simply is more complicated than translational motion, and therefore the Newton's first law in the world of rotation is fairly limited. There are lots of things that don't follow Newton's first law of rotational motion because they either change shape or because they're wobbling. To perfect the draft of Newton's first law of rotational motion, we need to identify the external influences, and we need better language to describe rotation about a fixed axis turning equal amounts in equal times. I'm going to start with the second task. In the previous episodes, I described translational motion and identified several physical quantities that are useful for that description. Among those physical quantities were position and velocity. In describing rotational motion, there are analogous physical quantities. There is a physical quantity describing angular position. Angular and rotational doesn't matter, but it's technically called angular position. And there is a physical quantity describing how angular position changes with time, and it's called angular velocity. So those are the two quantities I want to introduce. First, angular position. Angular position is an object's orientation. And instead of illustrating angular position using the seesaw, I'm going to illustrate it using my body. So, angular position will describe how I'm oriented. I'm going to start with a zero of angular position, which is the starting point, the zero. This will be my zero of angular position, the orientation that we all agree is the starting point. facing you. If I change my angular position, that means that I'm facing some other direction, like this, or like this, and like that, and so on. Well, how do you describe technically, quantitatively, those various other orientations? How do you do it? Actually, you need an amount and a direction. You need a vector. And here's how the vector, so angular position is a vector quantity, and here's how it works. First, the amount is an angle, the angle through which you have to rotate to go from the zero, namely facing you, to the orientation that you're trying to describe. For example, this. This is the one I'm going to try to describe, facing like this. And the angle that I have to rotate through to go from the zero to this is 90 degrees. From there to there, that's 90, 90 degrees, right? So this angular position is 90 degrees. But that's not enough. This is 90 degrees, and so is this, and so is this, all right? So there are a bunch of 90-degree angular positions. We need a direction as well. And the direction of an angular position is the axis about which the rotation occurs. For example, to rotate to this 90-degree angular position, I need to rotate about a vertical axis, as though I were a toy top being spun. So I'm being spun, there I go. So this is 90 degrees about a vertical axis. But there's an ambiguity. This is 90 degrees about a vertical axis, and so is this. They're both 90 degrees about a vertical axis. How do you distinguish them? Well, physicists and mathematicians distinguish them using a convention known as the right-hand rule. And the right-hand rule says that if you take your fingers of your right hand and curl them in the direction in which the rotation occurs, for example, if I'm going from this to this, the rotation is like that. Then look at my thumb. The thumb of my right hand points in the official direction of that rotation, downward. So in going from 0 to this, I rotated 90 degrees downward. On the other hand, if I go from this to this, my fingers have to be pointing the other way. My thumb is now pointing up. This orientation, this angular position, is 90 degrees up. So the ambiguity is solved by the right-hand rule. 90 degrees down and 90 degrees up. How about this? That is 90 degrees toward you, and this is 90 degrees towards me. Final word about angles. The angle part of angular position can be measured in various units. Up until now, I've been using the unit known as the degree. It's a familiar unit of angle. This is 0 degrees, 90 degrees, 180 degrees, 270, 360. Another possible unit of degree is the rotation. Full rotation. This is 0, quarter rotation, half, 3/4, full rotation. But the unit that mathematicians and physicists normally use to describe angles is neither of those two. It's the radian. And there are 2 pi radians in a full rotation, where pi is the mathematical constant, 3.14159, and so on. And that is the natural unit of angles. There are reasons why it's particularly useful in physics. Whether you use it or not, doesn't matter. Pick your unit of angle and stick with it, you're fine. So you can describe this angular position as 90 degrees down, or quarter rotation down, or pi over 2 radians down. They're all the same. That's angular position, but that by itself doesn't help us redraft Newton's first law of rotational motion. We need to look a little deeper, and we have to look at how angular position is changing with time. because when something is actually rotating, its angular position is evolving, changing with time, and we need the next physical quantity, which is angular velocity. Angular velocity is the rate at which angular position is changing with time. So right now, my angular position is not changing with time, so my angular velocity is 0. But if I begin to spin, then my angular velocity is no longer 0. For example, if I turn like this, I am now turning about 90 degrees per second. And the same right-hand rule applies. I'm turning such that my fingers curl like this and my thumb points down. This is an angular velocity of 90 degrees per second down. Also, pi over 2 radians per second down. Let me stop. Let me show you 90 degrees up. Here it is. All right. I could show you 90 degrees toward you, 90 degrees per second toward you, but I'm going to run out of ability to do this. But I hope you get the point that angular velocity describes how an object is rotating, that is how fast it's going through angles, and also the axis about which it's spinning, and finally, using the right-hand rule, the specific direction of its spin around that axis. So you should be able now to distinguish 90 degrees per second down from 90 degrees per second up. That physical quantity, angular velocity, will be useful in redrafting Newton's first law of rotational motion because we can rewrite the rotating about a fixed axis, turning equal amounts in equal times as having constant angular velocity. If I'm turning 90 degrees per second down and staying that way, my angular velocity is constant. All right, that brings us to the other task, which is identifying the external influences that show up in Newton's first law of rotational motion. And those external influences are twists. Technically, they're known as torques. A torque is the influence that upsets rotational inertia and therefore violates Newton's first law of rotational motion. We'll look more at torques, but just so that you know what a torque is, let me show you what happens when I exert a torque on this seesaw. To do it, I twist the seesaw. So I'll grab the seesaw from the front and I will twist. And suddenly, it changed its angular velocity. It started with an angular velocity of 0. Let's get 0 there. And it's now, at present, it is a rigid object. It's not wobbling. It's obeying Newton's first law of rotational motion. But if I come in with an external influence of the right type, namely a torque, while I'm exerting that torque, it is not following Newton's first law of rotational motion. It changed its angular velocity. So, we can now state Newton's first law of rotational motion in all its glory. A rigid object that is not wobbling and that is free of external torques rotates at constant angular velocity. That brings us to a question. What influence or effect causes the Earth to rotate steadily, turning once every approximately 24 hours? The Earth is rotating because it exhibits rotational inertia. It's experiencing essentially no torques, and therefore it rotates according to Newton's first law of rotational motion. Namely, it's a rigid object that is not wobbling and is not experiencing any external torques, so it rotates with constant angular velocity. That angular velocity is approximately 1 rotation per 24 hours about the North Pole, so that the rotational axis points from the center of the Earth up through the North Pole, and that's the way the Earth rotates. So we see a balanced seesaw is not necessarily motionless or horizontal. What we can say about that balanced seesaw, however, is that it exhibits rotational inertia. If it's motionless, it remains motionless. If it's rotating, it continues to rotate. Because it's a rigid object that's not wobbling, it exhibits a particularly simple type of rotational motion, namely constant angular velocity. So right now the angular velocity of this balanced seesaw is 0. But if I twist it, and during the twist it's not rotationally inertial, and so I'm violating Newton's first law of rotational motion by doing the twist. Here we go. I'll give it a twist, and now it's once again rotationally inertial. It's obeying Newton's first law of rotational motion. It's a rigid object that is not wobbling, that's free of external torques, so it rotates at constant angular velocity, apart from some air resistance problems here. But the point is, it's rotating right now not because something is twisting it, but because nothing is twisting it. And it is its nature, and the nature of objects in our universe, to keep rotating in the absence of twists. They keep going. That's rotational inertia. So, in a normal seesaw, that perpetual rotation isn't possible because during the rotation, even when it's balanced initially, it eventually touches the ground. And at those moments when it touches the ground exerts torques on the seesaw. It twists the seesaw and therefore takes it out of Newton's first law of rotational motion, violates Newton's first law of rotational motion, and new things happen. And those new things, basically the consequences of torques, are a subject for the next video.